Chapter 14, first video. The probability of an event is a long-run relative frequency. For any random phenomenon, each attempt or trial generates an outcome. An outcome is what happened on the trial. For example, each time we approach a stoplight, it is a trial, and the possible outcomes, or sample space, is pulling up and having it be a red, a yellow, or a green light. Excluding, the yellow blinking or green blinking, we're just saying all the possible options are red, yellow, or green. Instead of individual outcomes, sometimes we consider events, which are a combination of outcomes. For example, if a trial consists of rolling a die, the outcome would be 1, 2, 3, 4, 5, or 6. An event might be rolling a die twice and getting a 1 on the first one and a 2 on the second one. Or in just run roll, we could say getting a 2 or getting an odd one, in which case we're looking at getting a 2, 1, 3, or 5. So it's a combination of outcomes. If we want to know about combinations of outcomes, it helps if the individual trials are independent. If trials are independent, then the outcome of one trial doesn't influence or change the likelihood of another trial. For example, when we are waiting for the bus, the trials are independent, since knowing how long I waited in one trial does not affect how long I waited in the next trial. You could wait 5 minutes one day, but the next day it's totally different. There's a snowstorm, and you had to wait 25 minutes for the bus. Now you could argue dependence here, saying that maybe one bus route is always slow, but in our situation we're just going to claim they are independent. However, here's one that is always dependent. If we are drawing cards without replacement from a deck, the trials are not independent. If we draw a club on the first trial, then we know the next card is less likely to be a club and more likely to be a heart, a spade, or a diamond. This is why casinos use 6 decks for blackjack instead of 1. It prevents people from keeping track of which cards they've seen and betting smarter. The law of large numbers says that the long-run relative frequency of repeated independent events gets closer and closer to the true relative frequency as the number of trials increase. The picture below shows the relative frequency of heads after each of 100 flips of a coin. Notice how when there are a small number of flips, the relative frequency of heads can vary quite a bit from 0.5. But when the number of flips increases, the relative frequency gets closer to 0.5 or a half. So, looking at it here, if they only flip the coin 10 times, looks like they got a 55% chance of heads. So, they got 55%. If they flip the coin 20 times, okay, notice that their percent is a little less than 50. If they flip the coin 40 times, they're almost right on 50. And again, there's a little bit of a variation due to random chance, but the more you flip the coins, the closer and closer you get to 50% heads and 50% tails. So it's saying conducting the trial over and over and over again and looking at the average of the outcomes, or the relative frequency of the outcomes, it'll get closer to the true probability, because we know the true probability of getting ahead is 1/2. But it's very possible you get head, tail, 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 tail if you just did 1, 2, 3, 4, 5, 6 flips. But if you flip 100 times, by then the random chances kind of even out and you end up getting a probability where you end up with something closer to 50 out of 100 flips you got a head. It'll end up being closer to the true probability of 1/2. Many people misunderstand this law and apply it to situations with a small number of trials. For example, if we flip a coin 5 times and it lands on heads 5 times, heads, 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 well, the chance of getting a head on the 6th try is still 1 out of 2. But people think that it's higher because we had all these heads, so we're now due a tail. No. Okay? This is not true. Do not believe it. This is sometimes called the law of averages. Okay? However, since the trials are independent, the probability of the coin lands on a head never changes, no matter what has happened before. The law of large number only guarantees that the relative frequency of an event will approach the probability after a large number of trials. So again, if we did this flipping of a coin 1,000 times, then we're guaranteed it's going to be really close to 50% heads, 50% tails, maybe 448 out of 1,000 heads. Because by then we've done it enough times that we're less likely to have these streaks really matter. The coin doesn't purposefully compensate for its run of heads by landing on tails, but the results of many trials will eventually overwhelm any departures from what's expected. For example, we may start with 5 heads in a row, but after 100 more flips, we should be close to 55 heads and 45 tails. Okay? After 900 more flips, we should be close to something like 505 and 500. This is why casinos have boards which post the past 50 or 20 outcomes on a roulette wheel. The casino knows that gamblers misunderstand the law of large numbers and will be encouraged to bet more since they think they know what numbers will be more likely to come up. For example, if a lot of reds have come up, they're more likely to bet a large amount on black, assuming it's time for a black to come up. Chapter 14 is all about basic probability rules. I'm going to quickly read them to you. A probability is any number between 0 and 1, or 0% and 1%, and 100%. That is, for any event, the probability of event A occurring is between 0 and 1. Again, between 0% and 100%. Remember that a probability is a relative frequency. We cannot have more successes than the number of trials. So the probability of A always has to be less than or equal to 1. There can't be a 1.1 chance that something is going to happen, because if the probability is 1, it's a 100% chance it's going to happen. Also, we cannot have a negative number of successes. So again, it has to be between 0 and 1. An event has a probability of 0, then it will never occur. If an event has a probability equal to 1, then the event must occur. Something has to happen. That is, when we consider a single trial of random phenomenon, one of the possible outcomes must occur. For example, when we are flipping a coin, we must either get heads or tails. Yes, it could land on its side, but that almost never happens, so we just ignore it. Okay? All of the possible outcomes of a random phenomenon are called a sample space. So for a coin, it would be heads and tails. Thus, the probability of the entire sample space is equal to 1. Hence, the probability that something happens is equal to 1. If we add the probabilities of all possible outcomes, and it doesn't equal 1, then the assignment of probabilities is not legitimate. Okay, there may be a rounding error, or you've screwed up on figuring out the individual probabilities. 3. The probability of an event occurring is 1 minus the probability that it doesn't occur. That is, the probability of A is the same as 1 minus the probability of A complement. For example, if the probability of rain today is 10%, and the probability that it will not rain today is 90%, 1 minus 0.1. The event not A is called the complement of A, and is denoted A complement. It could also be A little comma or tilde A. All of those mean not A. Okay, last rule. For two disjoint events, A and B, means they can't happen at the same time. The probability that one or the other event occurs is the sum of the two events. That is, the probability of A or B, which again is given by the union symbol, is the probability of A plus B. And that only works if they're disjoint. If they're not disjoint, we have that probability of A union B equals the probability of A plus the probability of B minus the probability of the overlap, which we counted twice. So this is not disjoint. And this always works because for disjoint, it would be minusing 0. So this upper formula always works. Okay. Two events are disjoint if they do not share any outcomes. For example, suppose you randomly selected a registered voter and asked him which political party he belonged to. Since you can only register as a member of one party, being a Democrat and being a Republican are disjoint events. Disjoint events are also called mutually exclusive events. So again, you can see here, being in set A and set B are disjoint because there's no overlap, while here, set C contains 7 and so does set D, so they are not disjoint. All right, so this next step is some questions involving the probability of being a Republican, which is 0.4 or 40%. Oh, I should make that red. And the probability of being a Democrat is 0.5 or 45%. And the probability, and notice that that doesn't add up to 1 because there are independents, right, or Tea Parties. So there are definitely other options here. But we wanted to find out the probability of being a Republican or a Democrat. And I'm going to leave this up to you using the rules, and I basically outlined it for you. Okay, go ahead and try to figure out those two. And I will check that in the note check. Let's skip down to rule 5. For two independent events, A and B, the probability that both A and B occur is the product of the probabilities of the two events. So A and B, which would be A intersect B, is the probability of A times the probability of B. Recall that two events are independent if knowing the outcome of one does not change the probability of the other event occurring. For example, if we flip a coin and roll a die, the event heads and 6 are independent, since knowing the outcome of the coin flip does not change the probability that the die lands on 6. Thus, the probability of heads and 6, well, the probability is the probability of heads, times the probability of getting a 6. Well, the probability of getting a head is 1/2. The probability of getting a 6 is 1 out of 6. So the probability of having both things happen is 1 out of 12. This rule also works for more than two independent events. For example, the probability of rolling 3 6s in a row is the probability of 6 times the probability of 6 times the probability of 6, which is 1/6 times 1/6 times 1/6. You could say 1/6 cubed, but careful that you don't screw that up. And either way, the answer is 1 in 216. Pretty slim chance of that happening if you have a fair die. However, you cannot use this multiplication rule when the events are not independent. For example, if we have a class of 30 students and it has 16 females, the probability of selecting without replacement, that makes it dependent, 2 females is not 16/30 times 16/30, since these events are not independent. Knowing that the first person selected was a female changes the probability that the second person selected was a female from 16/30 to 15/29. So in this case, the probability of getting a female and then another female is going to be 16/30 times 15/29. And you could figure that out. All right, lastly, summary. When you want the probability of A or B, you should add the probabilities, assuming that they are disjoint. And when you want the probability of A and B, you multiply the probabilities, assuming that they are independent. If the probability of rain in Salt Lake is 50%, and the probability of rain in Provo is 50%, what is the probability that it will rain in both places? And right now, all I can say is, I don't know, because they are not independent. Right? If it's raining in Provo, that storm may travel and end up in Salt Lake. So it increases the chance that it's going to rain in Salt Lake City. So we don't know the probability that it'll do in both places. This will be continued on the next video.